Ladies and gentlemen, welcome back to Chapter 29 and Interference. Today, we are going to finish up with light, starting with something that we've already discussed, and that is Huygens principle. And that is the idea that every point on a wavefront acts as a source for new waves or new wave fronts. It is for this reason that a few other things that we've gone over are possible, namely refraction and diffraction, which in turn is responsible for the interference patterns that we've been witness to thus far. We called it refraction is how light bends as it goes from one index or one refractive medium into another. And how much the light bends depends on namely the indices of refraction of the medium that was in and the one that it's going into.
Now, the link to the video that I posted on the Chapter 29 lecture page that showcases Huygens principle is going to do a much better job than I can draw here. So go ahead and pause and take a second to look at it now. When you've finished, you can listen to me sort of narrate as it happens. You'll notice that there is an incoming wavefront on the upper portion of the image with a lower index of refraction, and as it goes from the air or whatever you have in the upper portion down into the water or glass or plastic that has the higher index of refraction, obviously the light is going to move more slowly, and that's going to be responsible for essentially one of those individual light photons, one of those particles, whatever you want to call it, one individual ray of light refracting towards the normal as the light slows down to go into the higher index refractive medium. There's this other thing called diffraction that we haven't really talked a whole lot about yet, but it's a slightly different kind of bending. However, as we will see, it is wavelength dependent, like the dispersion effect of several wavelengths of light bending as they go through a prism. But this time, longer wavelengths will bend more through diffraction than shorter wavelengths. Diffraction is when light bends or goes around edges or corners. And it's for that reason that when I say light is incident upon a narrow slit, the light is fuzzy and spread out on a screen some distance away. But for larger apertures, the shadow appears sharp. As light passes through the narrow slit, the light bends to go around the edges. The more narrow the slit, the greater the bending or the diffraction effect. Now, I posted a link, or a couple of links, to some videos for Chapter 29, most notably the ripple tank and the laser diffraction interference patterns. And it's pretty clear if you look at the latter portion of the ripple tank video, the one with the metal bracket, and definitely the one that has like the glass plate, you can definitely see that the ripples, the waves in the water, are bending around the edges of the glass plate. So that's diffraction. In any case, the ripple tank and the diffraction slit demos are linked on the Chapter 29 lecture page. If we put these two pieces together, they give us a complete picture of interference or interference patterns. Light from two sources or from 2 points on a wavefront or two different wavefronts, whatever you want to call it, superimpose or add together. Now, if the waves are in phase, of course, they're constructed, and if the waves are out of phase, they're destructive. We talked about this before. If we run light through two narrow slits, let's say we've got some incoming laser light here, right? And then we've got a slit, and then another slit here. Now, the light is going to move like waves out of these two different slits, and we can see here that they're going to overlap, and on some screen, some distance away, you're going to have an interference pattern where it's going to be like bright and then dark, and then bright and then dark, kind of like this, right? Bright, dark, bright, dark, bright, dark, and so on. But why does it make this pattern? Well, the first thing to notice is that if you look at, say, the laser interference pattern, the diffraction pattern video, there's a bright spot in the very center, right? That's where it's brightest. And then
there's a dark spot and then another bright spot and a dark spot and another bright spot and so on. Now, presumably, the light has to go the same distance to get to the middle from both of these slits, right? It's intermediary in between the two slits. On the other side, they do dark spot, bright spot, bright spot, just like on this side, right? And so on. So the spot directly adjacent to that point right here will be dark, because the light has to travel farther from here to get there than it does from here to get there. And presumably, the difference in path length from the bottom slit to the top slit is like half a wavelength. And so they're out of phase, right? They interfere destructively as opposed to constructively here in the middle. And then the light is going to have to travel one full wavelength more to get to this spot than the light from here does, and so it can interfere constructively again, right? So, why is there another broad spot on the other side? Same thing. This is going to take a certain amount of distance. This is going to be like one wavelength more, like longer. This path length is going to be one wavelength longer, and so they can interfere constructively there again as well. Okay, well, that means that we have a pretty good explanation for the bright spots, right, and the dark spots. Usually we say n lambda is equal to d sine theta, where theta is like the angle of incidence, right? That's theta, and d is the separation in between the centers of the two slits. Now what this means is that for one wavelength we get this extra distance, d sine theta, and if that distance is equal to an integer number of wavelengths, we get constructive interference. Here at the first bright spot, that's 1 lambda, right? 1 wavelength path difference. Here it's 2 wavelengths path difference, the next one would be 3, and so on. And that's how we get all these bright spots. But that's for 2 slits. Interestingly enough, if we have a somewhat similar kind of configuration, but instead we have a single slit with width d, we have a screen here. Okay, obviously, so light from this end and from this end are going to travel the same distance. Light from the middle is going to go there. Light from this part and this part are going to travel the same distance, and you're going to get a nice bright spot here in the middle, right? But the dark spot and bright spot are going to be spaced differently than if there was a single slit. Now, why could that possibly be? Well, let's think about if this path distance here is exactly 1 wavelength longer than this path distance. Well, so that means if this path length here was exactly 1 wavelength longer than this path length, right? If this is like n wavelengths, if this is n plus 1 wavelengths, right? Then these two could interfere constructively, right? But only the end points. Now consider, if you will, a point here in the middle, right? This would be like n plus a half wavelengths. This, because it's going to be out of phase by half a wavelength, it's going to interfere destructively with both the top and the bottom, right? So that's no good. Let's consider then, so the top and the middle are going to interfere with each other. The 2 points next to that are going to interfere with each other destructively as well. And these two destructively, these two destructively, these two destructively. And if we integrate over this entire surface, right, if we add up all of the little infinitesimally thin slits, we definitely get a dark spot here instead of a bright spot. So for single slit diffraction, this is the condition for destructive interference, whereas for double slit, this is the this is the interference condition for constructive interference. Funny stuff, right? Well, that's how it actually goes. You can see a nice video of that, of course, in the diffraction interference laser patterns video in the link on the Chapter 29 lecture page. There's also this interesting thing called Newton's rings. And there's also a link to that one as well, a video for the phenomenon known as Newton's rings. And essentially, if you shine a light down on top of a spherical lens like this, like a converging lens, it'll look like there are dark rings. Even though you're just shining light at a, if this is a side view, you're just shining light down at a lens like that. There are dark rings apparently. Well, why does that happen? Please take a moment to go ahead and look at the Newton's rings video in the link, so we have a better common frame of reference, because I know my art skills are not so great. In any case, the light has to pass through the lens, and the lens is obviously going to be thicker here in the middle than it is over there, right toward the end. And as the light passes through the lens, some of it is going to reflect back to your eye, right? So, some of the light is going to pass through the lens, right? Some of it's just going to bounce off the surface. Some of it's going to bounce, is going to go all the way through, right? And reflect off the glass plate here that the lens is on, and then go back to your eye. Now, this beam here, let me actually draw it a little bigger. So here's our lens, right? Now some light is just going to go and bounce off towards your eye. Some light is going to go all the way through and then bounce off and come back to your eye. Now, let's say that this upper beam has a certain path length, right, n lambda. Now, if this path length is n plus 1, n plus a half times lambda, let's say, right? If this path length is longer by half a wavelength, it's going to look like, well, the beam from the bottom and the beam from the top are going to interfere with each other, right? And it's going to look dark there. Now, that reason, this is going to be the same symmetrically for a certain region that is a certain fixed radius or distance from the middle. So it's going to look dark in a ring, essentially. There are going to be other places, of course. Let's say that this bottom now is n plus 1 lambda, right? Or this path length is going to be one full wavelength longer than the upper path length, and so they're going to interfere constructively, and that's the bright part in the middle, right, in between the dark rings. It's actually slightly more complicated than that, because when light reflects off a higher index of refraction, like this one, it actually skips half of a wavelength, right? So if the path through the air between the glass slides is a quarter of the wavelength, then we can get constructive interference. And we get destructive interference for half of a wavelength. It is for this reason that bubbles appear to shift in color, as light from some black body radiator like the sun that has every possible wavelength of light shines on the bubble. All wavelengths and colors are going to hit the bubbles, and some are going to be reflected from the outer surface, and some are going to be reflected from the interior surface. So here's our bubble. If we take a little piece and blow it up, so we've got just the membrane, right? Some light is going to bounce off the surface, and some light is going to go through and bounce off this part and get to your eye. Now, the upper one is going to have suffer a what do you call it? It's going to suffer an inversion by skipping half of a wavelength, and so it can interfere with the one at the bottom if this thickness is basically a quarter of a wavelength, because it's going to go a quarter, and then this is going to interfere with another half, right? So then we can get constructive interference. Funny stuff, right? Now, what does that mean that, or what does it mean that maybe bubbles will change color? Well, the thickness is not always set. Some of the material, whatever, the soap or whatever that you use to make the bubble can like move around the surface, and so the thickness will actually change. And so you'll only get constructive interference if it's the right wavelength or the right color of light corresponding to how thick the bubble is at that part. Interesting stuff, right? Now, we already said that light is actually two waves, one magnetic wave and one electric wave that oscillate together, both perpendicular to the axis or direction of propagation. The orientation of the electric field portion is generally referred to as this thing that we call the axis of polarization. Light from most common sources, like the sun or whatever, stuff from a light bulb, are all polarized randomly, meaning that the electric fields of all the photons are oriented in different angles at all the time. So when light from randomly polarized sources goes through a polarizing filter like sunglasses, then light that is polarized perpendicular to the axis of polarization in the filter, that doesn't get through. Let me show you what I mean. So let's say you have light from the sun, right? It's going to be polarized randomly in all possible directions, right? Now let's say we go through a vertical polarizing filter, right? This light goes through a vertical polarizing filter. Basically, only the light that's vertical is going to get through. Only the electric fields, or the light whose electric field portions are vertical, are going to get through the polarizing filter. This is probably a good time for you to look at the video that I've included on polarization so you can see what that looks like. But suffice to say that we usually use filters like this, vertically polarized, in sunglasses, so that when the light that bounces off the road, which is going to be polarized parallel to the roadway or horizontal, when the light bounces off the road and gets to your eye, it's going to be blocked by the sunglasses, right? So you don't get blinded by light bouncing off of the street in front of you while you're driving. In any case, if you take randomly polarized light and run it through a filter, basically you're going to lose about half of your light intensity going through it. And all of the light that survives is going to be polarized parallel to your axis of polarization on your filter. This is advantageous to us because we can block out things like road glare. Now, if light passes through one polarizing filter and then through another one, the light can get blocked or transmitted depending on the angle in between the axes of the polarizing filters. Let's say this one's vertical and this one's at like 45 degrees, right? So that the angle in between these is 45 degrees. So then whatever light is going to come through here is going to be, here's our filter, here's another filter. The light that comes through is going to be polarized parallel to this one. But wait a minute, doesn't that mean that we're just going to lose nothing then, right? That doesn't make any sense. Well, if you remember, we lost half of our light going through this filter. And there's a relationship in between the amount of light output and the amount of light input. If we're talking about the light here after it goes through one filter and the light intensity here after it goes through both. We call this Malice's law, and we say that the light intensity is equal to the initial light intensity times the square of the cosine of the angle in between the two filters, right? So if we're going to call this the light intensity after it goes through the first filter, I naught, or your initial intensity. I is going to be the intensity here after it goes through the second polarizing filter. And this angle theta here is the angle in between the axes of orientation of the two polarizing filters. Now you'll note that if this is 90 degrees. Cosine of 90 degrees is 0, right? And so if these are at 90 degrees from each other, basically you get nothing. So if you have polarized light that's totally vertical, and you had a completely horizontal filter, you wouldn't let a whole lot of light through, right? It would be basically nil. This is also how we see movies in 3D, because guess what's in 3D glasses? Yes, polarizing filters. Now, the reason that that works is you have a polarizing filter in one eye that's vertical, and you have a polarizing filter in the other eye that's horizontal. So when this special movie projector puts these two images on the screen, one eye can only see the one that's vertical and the other eye can only see the one that's horizontal, right? Now, you see one image through one eye, you see the other image through the other eye, and the reason that some objects appear to be closer or farther away is because our eyes have displaced somewhat, right? Our eyes are, a certain distance apart. Like you have a certain lateral separation in between your eyes. That allows us to have the perception of depth, right? Because we triangulate the position to things. Like if you look at something, right, and you put your thumb over it, right? Like if you were standing right here and you wanted to put your thumb over the 0, okay? You close one eye and you put your thumb over the 0, and then you switch eyes. It looks like the 0 is in a slightly different place relative to your thumb, right? Move just a little bit. Now, if you put it really close to your eye like this, right, like right up to your face, you close one eye, you put your thumb over the O, and then you close it and look over the other one. Your thumb appears to have moved much farther, right? Why is that? Well, it's closer to your eyes, right? Your thumb is closer to your eyes, and so it appears to move more when you shift eyes. Long story short, your brain interprets how much an object appears to shift when you look at it with both of your eyes at distance. And if you're making a 3D movie, the objects that you want in the foreground are going to be farther apart in the two polarized images, and the things that are going to be farther in the background are going to be closer together left to right. Right? That way your moviegoers will see the image of objects much closer or farther away than the screen itself appears to be. The word hologram comes from Greek, hologramma, meaning whole message. And really it's sort of an apt analogy if you want to think about it for just a moment. The image that a hologram gives a whole lot of detail, right? If you take a photograph that's like, 5 inches by 5 inches or whatever, then you have a certain amount of detail. But a hologram will give you essentially a 5 inch by 5 inch by 5 inch depth image. The only way for you to make a hologram is you need light from a coherent source, something like a laser where the beam is sort of collimated to move together. Now what happens is if you have some kind of, let's say you've got a holographic plate here, right? And here's the object whose image you want to encode in the hologram. Now you're going to have a laser, right? You have a laser, and let's say you got a mirror here, right? And you have like another mirror and a beam splitter, right? Something that will diverge the beam and make it wider. Now this laser is going to go through the plate here, right? And then it's going to hit this thing and it's going to bounce back. And this wave that comes back we call the object wave. And this wave that comes this way we call the reference wave, right? And these two can interfere with each other, and when they do, they make these funny little patterns that kind of look like two waves called fringes. And when you reconstruct the image with a coherent light source, like holding up to the sun or whatever, right, it can reconstruct the image with all of the depth information stored in these tiny little microscopic fringes. And so you can essentially get a whole image, a three-dimensional image, inside this tiny little flat two-dimensional plate. In any case, I hope you've enjoyed this video. I'll see you again soon for Chapter 30.